push that rock here with some cement. In this experiment, we're going to pour 4 balls out of this urn containing 10 balls, 4 of which are black. And pouring them means we're drawing them out without replacement. So you pull one out, you look at its color, you keep it. You pull another out, look at its color, you keep it, and keep going. And you're counting up how many blacks you get. That's the experiment. And this type of experiment is called a hypergeometric. More on that later. But first we need a sample space. What could possibly happen? Well, if we're counting blacks, we could just, we're only drawing 4 and there's 6 whites, so we could get all whites, which means no blacks. We could get 1 black, 2 blacks. We're drawing 4 times and there's up to 4 blacks, so we could even go all the way up to 4. So there's the sample space. Now this is not symmetric, so it doesn't really help us with the probabilities any. So let's ask a probability question. Well, what is the probability of drawing 2 black balls in this experiment? Well, first we want to get the, probability is always a fraction. It could be 0 if the numerator is 0. If the numerator equals the denominator, it could be 1. Otherwise, the numerator has to be smaller than the denominator, which means it's a proper fraction. So it's either 0, 1, or a proper fraction. Now, our denominator is the number of ways that I could choose 4 blacks from 10. So number of ways to choose 4 from 10. So, Pascal's triangle, go to the 10th row, 0, 1, 2, 3, 4. There's 210 ways to do that. Okay. Now, up here, I need to get 2 blacks, and I need to get 2 whites. When I draw four balls total, and I need 2 of them to be black, well, then I need 2 blacks and 2 whites. Well, how many ways are there to get 2 blacks from 4? And how many ways are there to get 2 whites from 6? Okay. And again, we'll go to Pascal's triangle. So to get 2 blacks from 4, 0, 1, 2, 6. And then 2 whites from 6, 0, 1, 2, 15. So it was 6 and 15. So 6 and 15. And so what is that, 90 over 210? And we can reduce, it'll be 9 over 21. 3 goes into both, so we get 3/7. Okay, so that's the answer to the question, 3/7. Okay. Now, let's get a probability distribution. That means, for the experiment, we want to know all the possible outcomes, 0, 1, 2, 3, and 4. And we want to know the probability of each outcome, which we already know this was 90 out of 210, which equaled to 3/7. So how are we going to get the others? Well, to get 0 out of the 210, we need the 4 choose none. Out of the 4 blacks, choose none of them, and out of 6 whites, choose 4 of them. So that's going to give me out of the 6, here's the 6th row, choose 4, 0, 1, 2, 3, 4, 15. So that's, and always the 0th entry is always 1. So 1 times 15 over 210. So 15 over 210. Now if I reduce, clearly 5 will go into both, and then 3 will go into both. So 15 should go into 210 evenly. I don't know how many times, so we'll do this one at a time. So 3 goes into this 5 times, and 3 goes into this 70 times. So I have 5 over 70. And then 5 goes into 7 once with 2 left over, so 14, 1/14. Okay. Now, for here, we're going to do the 10, choose 4 in the bottom again, but we're going to choose 4, choose 1, because we want 1 black out of the 4. And then that means out of the 6 whites, we need 3, because we're getting a total of 4 balls, so we need 3 of them to be white if 1 of them is black, right? 4 balls, and if 1's black, there's 3 whites, okay? So then, again, we know the denominator, right, is 210. And then the first entry is always the row you're on, right? So if I'm on row 4, this is the 0th entry, so that's the first entry. So there's 4 here. And then the third entry on the 6th row is 0, 1, 2, 3, 20. So that gives me 80 over 210, which is great. If I reduce, that's 8 over 21. Now for 3, same thing. I need 3 of the 4 blacks, and I need 1 of the 6 whites out of the total number of ways to choose 4 from 10. So I get 210 down here, and 4 choose 3 is going to be back to the same thing as 4 choose 1, because the triangle is symmetrical. 4 choose 1, 4 choose 3. So 4. And then 6 choose 1 is 6, because remember the first entry is always the row you're on. And so I get 24 out of 210, which 3 goes into both. 8 out of 3 goes into 70 times. And then 2 goes into both. 2 goes in that 4 out of 35. Okay. And then finally, we're going to choose 4 blacks out of the 4. And then that means we need 0 of the whites. Now notice these bottom 2 numbers always add up to the sample size. 0 plus 4 is 4. 1 plus 3 is 4. We already did 3 plus 1 is 4. 4 plus 0 is 4. And then the top 2 numbers always add up to the population size. There's a population of 10, so 4 plus 6 is 10. 4 plus 6 is 10. 4 plus 6 all the way down. Okay. Now, the 4 choose 4 is 1, and 6 choose 0 is 1, so we have 1 out of 210. Now, if this is, if we've done this correctly, all of the probabilities should add up to 1. So we have, this was, what was this, 15 out of 210. I'm going to use the ones with a common denominator. And then 80 out of 210. And then 90 out of 210. And then, what is that, 24 out of 210. And then 1 out of 210. Okay, so 80 and 90 gives us 8, 9 is 17. So there's 170 right there. So 170. And then we have 15 and 24. Well, that's going to be 39 plus 1 is 40. So 40 and 100, sure enough, that gives me 210 out of 210, which is 1. So that's a nice quick check to see if you did your math right. Is add up all your probabilities and see if they add up to 1. They should. Okay, now this whole deal is called a hypergeometric experiment. So we're drawing without replacing. Sampling without replacement creates a hypergeometric experiment, and we want to know the hypergeometric probability distribution formula. Well, in it you have to have a population size. So in our example, n was 10 because there were 10 balls. You have to have a sample size. Well, it was 4 because we were drawing out 4. You had to have number of successes in the sample. Well, that's your variable. You could have 0 successes, 1 success, 2 success, 3 success. So that's the variable. So the probability that x is some number. Okay, and then you had to have a number of failures in your sample. That's also, a variable, because if you choose 0, well then, and your sample size is 4, well then there's going to be 4 failures and that sort of thing. So what was the formula? Well, we already kind of figured it out. It was n, choose n, down here. So we're the sample size from the population size. Then up here, it was from your number of, actually I need to know how many, if we're counting blacks, I need to know how many are in that. So I don't really have enough. So x is going to go here, and then n minus x is going to go here, okay? But I need to know how many are black or whatever. So we're going to say I need to have, let's call it k. I think most books call it k. And that's the number of blacks, which in this case is successes, in the population. Okay, so that helps me finish off this thing. So I'm going to have x choose k from k, x successes from the k successes in the population. That makes more sense. And then what is this? Well, if there's k successes in the population and there's a total of n in the population, then it's n minus k goes here, because that will be the number of failures. So when this was 10 and this was 4, 10 minus 4 gave me 6, okay? So notice that this plus this, the k and the negative k cancel, and it gives me the sample, the population size. And then this plus this, the x and the negative x cancel, and gives me the sample size. So that's a way to check yourself. This plus this should be n, and this plus this should be lowercase n. So this plus this should be population size, this plus this should be sample size. That's the hypergeometric probability distribution formula. Math made simple. Some math.